Friends, this possibly would be the last of the series of lectures that I have been delivering on heat transfer. Today we will be studying the internal flows with reference to development of flow in terms of the thermal boundary layer. Okay. So we'll be looking at what we call as the thermally fully developed flows and try to understand the behavior of the development of the thermal boundary layer inside ducts and what happens in the fully developed region. We'll try to look at the energy balance in that region and look at the orders of magnitude of various terms in the equation and hence derive expressions for the Reynolds number in the fully developed region. We'll be looking at two different types of boundary conditions: when the duct has constant surface temperature or when the duct has uniform heat flux on the surface. What does the expression of a Reynolds number look like? And then we'll finish the course with understanding what happens when the flow becomes turbulent, what happens in the region that is developing before the region of fully developed region. What we have been looking at expressions as for fully developed region. So what happens in the developing region, and then we will also briefly look at what happens if the duct that is there has different shapes. We have been looking at parallel plates channel, we have been looking at circular pipes as examples, but the ducts can be of any other arbitrary cross section also. It can be a square duct, it can be rectangular duct, various things. How do you calculate then the fully developed Reynolds number or the developing Reynolds number for that matter in such cases? So that is the list of topics that we will be approximately trying to cover in today's class. In the previous class we actually looked at the development of the hydrodynamic boundary layer and therefore hydrodynamically fully developed flow in a duct, and we said that in the region where the flow is fully developed, the pressure becomes linear, that is dP by dx becomes constant, and that dP by dx is equal to the d square u by dy square, the velocity profile's second gradient multiplied by the viscosity or rather viscosity multiplied by the dP by dx, or 1 by mu multiplied by dP by dx is equal to the second gradient of velocity. Using this we obtained the solution and said that the velocity profile in the fully developed region is going to be parabolic. So if the flow enters the duct as a flat velocity profile, by the time it fully develops, it develops into a parabolic velocity profile. And in that region we also said that the expression for skin friction coefficient can be reduced, and we can write the pressure drop as a function of rho u squared using the skin friction coefficient Cf or the Darcy friction coefficient F, which are related by a relationship as F is equal to 4 times Cf. Right. So with that we learned how to calculate pressure drops in fully developed regions, and we also looked at what is the minimum distance required for the flow to become fully developed from the arguments of the boundary layer thickness as a function of x, and found that the L by 2h, which is the length for full development divided by the cross-sectional dimension, would be 5% of the Reynolds number for the flow to fully develop in laminar flow. Okay. In turbulent flow we just mentioned that it could be 10 to 60 times the cross-sectional dimension in the case of circular pipes or in the case of parallel plate channels. So this is something that we had talked about in the previous class. In today's class we will be looking at the development of the thermal boundary layer. So in order to consider the case to be simple, what we will assume is that at x is equal to 0, where the temperature of the incoming stream is uniform and is different from the wall temperature, the velocity profile is already fully developed. So we will be saying that the velocity profile throughout the argument when we are looking for development of thermal boundary layer is unaltered, because when both of them are changing, the flow becomes a little bit more complex, we'll deal with them separately. We don't need to deal with them in this course, but normally we deal with them separately, calling the flow simultaneously developing hydrodynamically as well as thermally. In this particular course, we'll basically look at the hydrodynamically fully developed flow and look at only the development of the thermal boundary layer. Okay, so the velocity profile is always a parabola, and therefore the u is only a function of y and independent of x, and v is 0. So that is the thing which we take from the results of fully developed flow in hydrodynamically fully developed flow, and argue only about what happens when the thermal boundary layer develops. So let's go to the whiteboard and try to understand that part. So we said that in a duct, now we are considering hydrodynamically developed flow. So the velocity profile right at the inlet is a parabola. So you can say for if it's a parallel plates duct, so this is a duct of parallel plates with 1 meter in the depth direction perpendicular to the plane of the paper. This is x and this is y. This direction would be z. We'll not bother about variations in z direction. We'll only say that the plate is infinite extent in the z direction, and therefore the and this is y is equal to plus h and y is equal to minus h, and so the cross sectional area for the flow would be the 2h, which is the distance between these two plates, multiplied by 1 meter in that distance. So the cross sectional area would be 2h multiplied by 1, and the perimeter for this flow will be only on this side and this side 1 meter each, so it will be P would be 2 meters. So whenever I calculate area by perimeter, it will be h. Okay, so that is the thing that we'll be looking at for this plate. So this is the parallel plates channel that we are looking at, and the velocity is fully developed at all points in time. Now at x is equal to 0, so if this flow initially has a temperature of, let us say, Ti, okay, at the inlet, then this is the mean temperature. Okay, the mean temperature is equal to Ti at the inlet, and the wall temperature can be varying from here. So from this location onwards, that the plates are given a different boundary condition as compared to the Tm. The plate temperature is not equal to Ti, but is different from that. So there can be two different kinds of cases, or more the more kinds of variety can than that. One of the possibilities is that the wall temperature in this entire region is T wall, which can be greater than or less than Ti. So it is what we call as the constant T wall or constant wall temperature. The other possibility is that you can have a uniform heat flux throughout this plate. Okay, so throughout the top plate and throughout the bottom plate, I can have uniform heat flux. So you can have a constant Q dot double prime wall. Now, what we will be considering in terms of thermal development is not specific to one or the other. We will be considering both the cases simultaneously. In the sense that we will not assume that Q wall or T wall is constant. So in the more general case, the T wall would be some function of x. Okay, so the T wall would remain some function of x, and so it is not constant with x necessarily. Okay. So we'll then be taking infinitesimal elements of this and then looking at the energy balance. So let us try to first understand what happens for thermal development. So there is a thermal boundary layer that starts developing at this location. So if I just look at the two-dimensional cross section of this is the inlet section at x is equal to 0, and from here the thermal boundary layer starts developing, just like the hydrodynamic boundary layer, and at some length LDT, which is the thermally fully developed length or thermal development length, the two boundary layers would meet, and after that there is no distinction between the boundary layer and the interior. What happens in this period? Suppose the wall temperature is higher than the inlet temperature, then in between this, the temperature is still unaffected by the presence of the wall, and between the wall and the edge of the boundary layer, the temperature has gone higher than Ti. So this can be boundary layer temperature like this. Okay. So this is the way the boundary layer develops. So here it is all uniform. So here it's like this. Here it's like this. Here it's like this, and finally it becomes some profile like this. Now, in the case of constant wall temperature, it is easy to visualize. This temperature is constant and this temperature is constant. So between those two temperatures, the profile becomes this. And after full development, the heat transfer is still happening, and therefore the centerline temperature would still be changing. The centerline temperature would not become a constant after full development. The centerline temperature would still be changing. So in that sense, it is different from the hydrodynamically developing flow. Okay, and even if T wall is fixed, the T wall minus T center would keep on decreasing as the flow goes, and when the length tends to infinity, you would get a uniform profile with all T wall. Okay, that is at length tending to infinity. But in between, there is still further heat transfer happening, and therefore the temperature profile does not become a constant. Okay, but something else happens when the boundary layers meet. We'll understand what happens by analyzing the equations at that point. Now, even if the heat flux is constant, in which case the wall temperature will continuously be changing from the inlet onwards, and the bulk temperature would also be changing. So there will be a dynamic equilibrium between the heat that comes in and the temperature profile that changes. So basically, we'll need to understand, okay, there is a developing region and there is a fully developed region. First, let us concentrate on the fully developed region and try to understand what all can happen in that region. Okay. So let us first consider thermally fully developed region. Okay, we have said that the flow is already hydrodynamically fully developed at x is equal to 0. So even before the thermal boundary layer begins, the flow is hydrodynamically fully developed. Now let us look at in the thermally fully developed region, that is in a region which is after this LDT. Okay, so we take a small section in this region and try to understand the energy balance of that region. So suppose I can define a mean temperature across the section of the duct. That is, there is a certain temperature at the wall and there is a certain temperature inside. There is a variation. So if I can define a certain mean temperature, this mean temperature would be changing with x depending on the extent of heat transfer that is happening. So how to define the mean temperature? This mean temperature can be defined as suppose I say m dot Cp is the mass flow rate and specific heat of the substance that is flowing through the substance through the duct, then m dot Cp Tm would actually be an integral from y is equal to 0 to h, okay, multiplied by this will be actually twice that, because 1/2 is integral from 0 to h, so twice of this, integral of rho u at any y into Cp, this multiplied by dy. Okay, because the area is dy into 1 because there is a unit depth. So this is rho u Cp dA. Okay, rho u dA is the dm, the d of m dot, mass flow rate through any elemental segment. So if I look at this duct and I divide it into, so it will take one plane and take one small elemental strip on that at any given y with the width of dy. Okay, the area of that will be dy multiplied by 1 because that is the unit depth. Okay, and if density is rho and u is the velocity at any y, then rho uy dy will be the mass flow rate that goes through this. That multiplied by Cp into T will be the amount of energy that is flowing through that. This integrated over from 0 to h will be half of the energy. Then that multiplied by 2 will be the full energy. So that is what we are trying to do here. So this multiplied by the temperature at that location. So this integral would be equal to this. So now if I write this m dot in itself is nothing but integral from 0 to h multiplied by 2 of rho u dy. Okay, so m dot Cp will be, there will be a Cp here. So what will this be? Tm will therefore be equal to, so the 2 would get cancelled between the 2, it will be integral of rho u Cp T dy divided by integral of rho u Cp dy from 0 to h. Okay, so this is the definition of mean temperature. This temperature is called T mean, or it can also be called as T bulk temperature. So that is the temperature of the average temperature of the bulk of the flow. It's also called the mixing cup temperature. So basically, to conceptualize it, like the flow at any section of the thing, if I take this entire flow and put it into a cup and mix it thoroughly, then the temperature of this cup would be the mean temperature. So that is basically what we mean by this. So the mean temperature can be defined at any section. So as we go from the inlet towards interior of the flow, because there is heat transfer taking place through the wall, this mean temperature will continuously change. Okay, so then if I look at the energy balance in the thermally fluid enveloped region, then suppose there is this duct and I take a small segment of distance dx. Okay, then suppose this is Tm at the inlet of this, and at the outlet of this dTm plus Tm is the temperature that is at the outlet of this. Then suppose there is a certain amount of heat flux that has entered q dot double prime at wall. So then the energy balance would basically say that m dot Cp into Tm plus dTm minus Tm. So this will be the rate of change of the energy contained in unit mass flow of this one, so multiplied by m dot. So the total energy contained in the stream between these two segments, the difference. Now this should be equal to the amount of energy that entered the duct through this, which will be actually q dot double prime at the wall multiplied by the area, which is going to be equal to the perimeter multiplied by dx. Okay, where P, capital P, is the perimeter. In this case, for a parallel plate duct, it will be just equal to unit depth, which will be 1 multiplied by dx. Okay, on this side, so 1 plus 1 will be 2. This is your expression. Now this m dot can be written as rho u a, and where this u is the mean velocity u bar. Okay, this m dot can be replaced with this expression. So if I do that, then I'll be able to cancel out this Tm and say dTm by dx is equal to q dot double prime at wall, okay, divided by rho u bar a Cp, okay, and there is a perimeter here. Okay. So this is basically that. This dx will go down here, and so you get dTm by dx is equal to q dot into perimeter divided by rho u a Cp, and now we can combine this as q dot double prime at wall divided by rho u bar Cp multiplied by a by p. Okay, so this is the term that we try to define for a parallel plates channel. For a parallel plates channel, we define it as equal to h, because the area of cross section here is 2h multiplied by 1, and the perimeter is unit length on both sides, and there is nothing on the sides, so this is 1 plus 1, 2. So 2h by 2 will be h. So that is what we have defined for a parallel plates channel. Suppose I have a circular pipe, then the area is pi d squared by 4, and the perimeter is pi d, so you get a d by 4 as the area of the perimeter. So depending on the cross-sectional area, the area of the perimeter will vary. So this expression is general, and this does not assume anything. This q dot can be a function of x, so it's not considering q dot as a constant. The t wall can be a function of x. So for any kind of boundary condition in the thermally developed region, this can be written. That is, the dTm by dx is equal to, and this is actually also valid in the region before full development, but definitely also valid in the region in full development, because this is something which does not assume anything about the t wall or t mean or anything. All of these can be functions of x as the case may be. So this is an expression. Now using this, let's look at the fully developed region. So when I say fully developed region, now I am looking at the thermally fully developed region where the boundary layers have already met. So what happens in that? Of course, since it is hydrodynamically also fully developed, u is only a function of y, and therefore del u by del x is 0, and v is identically 0. Okay, so these two have already been considered. And in the region where it is fully developed, what happens is the temperature varies substantially with y, but with x the variation may not be that much. You can do an order of magnitude and say that y is of the order of h or 2h, and x is of the order of L, which is much greater than h, because the flow is fully developed, so it has gone through a certain distance, and this L is larger than h. So if you write this equation, u del t by del x plus v del t by del y, whole thing multiplied by rho Cp, is equal to k into del squared t by del x squared plus del squared t by del y squared. This is your convection diffusion equation for two-dimensional case. So in this case, if I try to normalize, I can do that. If I say theta is t minus t mean divided by t wall minus t mean, I can do this, or even I can just keep it as t itself, just normalize the length with respect to L. Then I'll get a x here, which is x by L, which is of the order of 1, and I'll get a y here, which is y by L, which is of the order of h by L, which is much less than 1. So in this case, this term will become small and negligible as compared to the del squared t by del y squared term. That's an order of magnitude I will do. So I can drop the second gradient term in the right hand side because it is small as compared to the other term. On the left hand side, I know v is 0, so this term gets struck out. So this equation becomes rho Cp into u del t by del x plus is equal to k del squared t by del y square. This equation is now simplified by neglecting one term on this side and one term on this side. So this is the equation that is applicable in the fully developed region. Okay. So the assumption for full development is that v is 0 for hydrodynamic full development, and del squared t by del x squared is negligible as compared to del squared t by del y squared in the thermally fully developed region. So those are the assumptions that we are putting. So this equation is correct. Now let us do an order of magnitude analysis. This del t by del x in the fully developed region is going to be of the order of this dTm by dx that we derived here. Okay, so the order of magnitude of the rate of change of temperature at any x would be the same as the rate of change of the bulk mean temperature. So that is the assumption that we will take. So this we will say is of the order of dTm by dx. Okay. So what will happen to the left hand side? Then you can also say that this u is of the order of u bar. So then the order of magnitude of the left hand side, we'll write rho u bar Cp into dTm by dx, which is the left hand side, and this can be now simplified further. dTm by dx, you substitute the expression that we had already derived. So the rho u bar Cp would get cancelled between the numerator and denominator, and you will get the remainder. So this will be rho u bar Cp multiplied by q dot double prime at wall divided by rho u bar Cp into A by P. Okay, so this rho u bar Cp would go, so it actually become q dot double prime wall divided by A by P. Okay, so the left hand side is of the order of this q dot double prime wall divided by A by P. What happens to the right hand side? The k times del square T by del y squared is the term that we have on the right hand side. This is of the order of, let's keep the k, this is del by del y of del T by del y, and this del T by del y, since the flow is across this, I can say Tm is the temperature in the interior and T wall is the temperature on the surface at any given x. Both of these can be functions of x. Okay, now at any x, this del T by del y is of the order of T wall minus T mean divided by h. Okay, because this is 2h and the mid distance is h. Now this del T by del y can be said of the order of T wall minus T mean divided by h. So this itself, the k del by del y of this can be said to be of the order of, this y itself is of the order of h. So you can say it can be k times T wall minus T mean divided by h square. Okay, so this is the right hand side, which is of the order of k into T wall minus T mean by h square, and this, since is of the order of the left hand side, this is of the order of q dot double prime wall divided by A by P. Okay, now for the circular duct, A by P we said is of the order of h, so this q dot double, sorry, for a parallel plate channel we said it's of the order of h, so it is q wall divided by h. Okay, now this q dot wall in convective heat transfer is normally written as h multiplied by T wall minus T mean. Now this all can vary with x, so this is also a function of x, this is also a function of x, and this is also a function of x. This can be in the most general case. So q wall is written as h into T wall minus T mean. So if I substitute that here, this becomes of the order of h into T wall minus T mean by capital H. Okay, so this is your expression that you get. So if I take this is of the order of this, I can write h into h by k is of the order of 1, because this T wall minus T mean gets cancelled between this side and this side. Okay, and then I get this 1h would also get cancelled. So I would be able to say h into h by k is of the order of 1. So if I call this as the Nusselt number, where the length scale is of the order of the cross-sectional dimension, h into h by k. Now this Nusselt number is of the order of 1 for a fully developed flow. So the only assumption that we made, it is a fully developed flow. We have not made any other assumption with respect to what the boundary conditions. We have not said constant wall temperature or constant wall flux or whatever it is. So any thermally fully developed flow, we say that the Nusselt number is independent of any other parameter and it becomes of the order of 1. That is the result that we get. This is a very interesting result, because irrespective of whether it's constant wall temperature or wall flux, when the flow is fully developed in laminar flow, the Nusselt number becomes a constant which is of the order of 1. So this is basically what we get as an interesting result or important result. So what is the definition of full development then? Because we have been groping for that what becomes constant. So we say thermally fully developed flow means Nusselt number is a constant. Okay, or Nusselt number is also h into the cross-sectional dimension by k. Okay, so this is a constant. Since the cross-sectional dimension and k are not changing, it actually means that the heat transfer coefficient becomes a constant. So whenever I say thermally fully developed flow, nothing else is becoming constant. It's actually the heat transfer coefficient that is becoming constant. So this is the first understanding that we get from the whole analysis that we did, that when the flow is thermally fully developed, we say that the heat transfer coefficient becomes a constant. Okay. Now let us look at the variants of this one. So when I say one of the simplified cases of the thermal boundary layer is a constant surface temperature T wall. Okay, so what happens? Suppose I have a duct whose wall temperature is T wall, both sides, and there is a flow that is coming in with some inlet temperature Ti. Okay. So it has a constant temperature in this region. So the wall suddenly goes to T wall. Okay, so this is the temperature that you have. T wall, let us say, is higher than Ti. So the wall temperature is this. At the inlet section, you have this profile. But as this flow goes in, the T wall remains the same, and the flow starts becoming this and this and this, and finally the T wall would eventually, as T tends to infinity, the entire T mean becomes T wall. So if I try to plot as a function of x the temperature, the T wall is a constant. This is T wall. Okay, so let the T mean be equal to Ti here. Okay, so as the flow goes, the T mean will gradually tend to approach T wall and become at T tends to infinity, they will go. So if the development length is somewhere here, so let us say the development length is somewhere here, beyond LDT, what we will see is that the H becomes a constant. Okay, so what is this? You have a Q dot wall double prime is equal to H into T wall minus T mean. So in this, what will happen is that this H will become constant. So this T wall minus T mean will directly become proportional to this, and as T wall minus T mean diminishes as x increases, this Q wall will also diminish in an exponential fashion as it is shown here. Okay, so the analytical solution of the equation that we started with, this equation, if we try to solve this analytically with the boundary condition that the T is equal to T wall on the walls, and the T is the dt by dy is 0 at the center because of symmetry, and T is equal to Ti at the inlet, and as T tends to T infinity, the T becomes equal to T wall. When the boundary conditions are imposed like this, and this equation is solved by variable separation method, you get the solution for the fully developed region. Or you can actually say that dt by dx. Okay, so this analytical solution would basically yield an exponentially varying temperature with x. The temperature would exponentially approach or asymptotically approach T wall, and that is the solution that you will get. So what you will find is that this Q dot wall is continuously changing with x. In the beginning, both H as well as this are changing, but after the distance of LDT, the H stops changing and it becomes a constant, and only T wall minus T mean is changing. So if I plot H as a function of x, what will happen? The gradient of temperature, of course, is higher at the inlets, and therefore the H value would be higher, because what do you define H as? This is actually equal to A del T by del Y at H, right? So this del T by del Y is very high. It's infinite at the inlet because there is a sudden drop in temperature from T wall to Ti, and as you go inside, the gradient gradually comes down. So this H is infinite at the inlet and it gradually comes down. So if I plot the heat transfer coefficient as a function of x, let me draw it here, H as a function of x, it actually starts from infinite and becomes drawing. Okay, so it becomes a constant after LDT, and before that it exponentially decays like that. So this is your plot of H as a function of x, and what we can find from the analytical solution is that this H fully developed is actually equal to 3.66 for laminar flows with constant wall temperature. Okay, so this is a number which is of the order of 1, and it actually settles down to 3.66. Okay, so fully developed H in constant wall temperature case is 3.66. What happens in constant wall flux case? Okay, this we could call it as CWT or CST case, constant surface temperature or constant wall temperature case. In the case of constant wall flux, what happens? if I look at the variation of temperature with x, the mean temperature, because the heat flux is constant, at every unit distance the amount of change in temperature would be the same if the properties are the same. So the mean temperature would increase linearly. This is Tm. Okay. At the inlet, T mean is also equal to Ti. So at the inlet it is here, and there is a more rapid variation of T wall in the beginning, and after that it becomes constant. Why does it become a constant? So this is T wall and this is T mean. This is in contrast with what you plotted here. Here the T wall was a constant and the T mean is asymptotically approaching it. In the case of constant wall flux case, since Q dot double prime wall is H into T wall minus T mean, and in the fully developed region H becomes a constant, and Q wall is already a constant, so T wall minus T mean also becomes a constant. So this difference becomes a constant in the fully developed region. So this is somewhere LDT. So in the region before LDT there is a variation in T wall minus T mean because the H is still varying. The Q wall remains constant throughout. Okay. So after LDT, because H becomes a constant, T wall minus T mean also becomes a constant, and the difference between these two would be dependent on the magnitude of Q wall because the H becomes a constant. So if I plot H as a function of x, the same LDT, it becomes a constant, and before that it starts from infinity and comes here. So this is the same variation that you have, but now this number is 48 divided by 11. Okay, so that is the number that you get for constant heat flux, which will be something like 4.36. Yeah, so this is 4.36 for the case of constant wall flux. Okay, so in laminar flow and constant heat flux boundary condition, the fully developed Reynolds number becomes a constant equal to 4.36, whereas in laminar flow with constant surface temperature boundary condition, the fully developed Reynolds number becomes 3.66. Both of these are of the order of 1 and independent of any other parameter. It's not dependent on the Reynolds number, it's not dependent on the Prandtl number, it just becomes a constant. Okay. So this is the behavior of thermally fully developed flows in laminar flow. Okay. And you can have any other kind of boundary condition also. You can have, for example, a Q wall that is linearly varying with x, or you can have T wall that is a function of given function of x. So for each of these cases, there will be a development length after which you will have a constant h. And the constant h will neither be this nor be 3.66, but it will be some other value depending on the kind of profile that you have. But it will have a constant h so long as the boundary layer is laminar, or the flow through the duct is laminar, and the flow becomes fully developed after a certain distance. Okay, where the two boundary layers have met. So the only characteristic that you can specifically say about thermally fully developed flows is that it has a constant heat transfer coefficient H. So that brings us to the end of the discussion on laminar laminar fully developed flows, thermal boundary layer development inside the ducts. Okay. And we have also seen what happens in the region where the development is happening. The heat transfer coefficient is higher than the fully developed heat transfer coefficient. Okay. In the same way, we can also say for the hydrodynamically developing flow, okay, we said that with x, the dp by dx becomes a constant. Okay, so at the inlet, the dp by dx is going to be much higher, so the dp by dx also varies in this fashion, and this dp by dx will eventually go to a constant which is going to be equal to Cf times area by perimeter. Is that correct? Cf times the area by perimeter. So L divided by A by P into half rho U bar squared. Okay, so this is the expression that you will get for dp by dx after the flow is fully developed. So not this L. This L is coming after the integration of so this will be 1 by A by T. This is your expression for dP by dx. So the dP by dx also becomes a constant in the fully developed region, but before full development it is higher than this. So you can say that the velocity gradients are sharper in the developing region, and therefore the dP by dx is higher. So if I am looking at a fully developed region, I can take a constant Cf and work with this, but the Cf is higher than this fully developed Cf in the developing region. So if I have, for example, a pipe which is 25% developing and 75% developed, the pressure drop will be more as compared to a pipe which is 100% fully developed. So that is the difference that you will need to see. So whenever you neglect the developing region, you should understand that you are neglecting a region which has a higher pressure drop per unit length. Okay? So that is the thing that you will see. In the same way, in heat transfer coefficient also, if you are neglecting the developing region and saying that the pipe is fully developed practically throughout the length, then you are actually neglecting a region which has a higher heat transfer coefficient as compared to the rest of the pipe. Okay? So that is basically the thing that you need to understand. The development length itself, LDT, we can do similar arguments like we did in the earlier case. The value of LDT can be evaluated as approximately 0.05 times REPR. So this is the expression that you will take. So in the case of parallel plates channel, this RE will be RE2H, which is rho u bar into 2H by mu. In the case of circular pipes, it will be RED, which will be rho u bar d by mu. Okay, so this will be the thing that you will get. The development length can be estimated for thermally for fully developing of the flow as 0.05 times REPR. Interestingly, the power of the PR does not change with Reynolds number; it just remains REPR as together. So the thermally developing length can be estimated by this. So if the actual length of the pipe is much larger than LDT, normally you consider the flow to be fully developed throughout the pipe, neglect the LDT and calculate the heat transfer. But if the pipe length is comparable to the developing length, this is again in laminar flow. So in laminar flow, when the Reynolds number is less than 2300, we take the flow to be laminar, and in such a case the development length can be estimated by using this. Okay, so now what happens when the flow becomes turbulent? So in turbulent flow, so if I take in laminar flow, the velocity profile has to become parabola in order to have the flow fully developed. In the turbulent region, because the gradients near the wall are much sharper, this is laminar fully developed flow, velocity versus, so this is y versus u. In turbulent flow, in comparison, the boundary layer profile is rather flatter. So this is the kind of velocity profile that you will get. Okay. Rather than an elongated profile like this, if I plot over this, it will come something like this. So the gradients are sharper near the wall, but in the interior, the flow is rather reasonably uniform. It's not exactly uniform, but it's less curved as compared to the laminar flow. Okay, so this is your turbulent fully developed velocity profile. So you may guess that if I start from a flat profile and you have to get to a parabolic profile, it actually takes a lot more development. But if I need to get to rather flattish profile, the length for development is shorter, and that's exactly what happens in turbulent flow. The length that is required for the flow to fully develop only varies between 10 to 60 in the case of turbulent flow, and the length is shorter as the flow becomes more turbulent. Okay, let us say I take Reynolds number is equal to 10,000, then it will be closer to this end. But if I take Reynolds number equal to, let us say, 50,000, then it will be closer to this. Okay. Whereas for laminar flow, let us say Reynolds number is 2300, then 0.05 times Re, okay, would actually be 0.05 times this, which will be 125. Okay, so you can look at the comparison. This is the number of, this is actually the comparison of L by LDH by D, or LDH by 2H, let us say, is a maximum of 125 in laminar flow. Okay, but when it goes to turbulent flow, it jumps to about 60 in the range of Reynolds number of about 10,000. This is the upper limit of laminar flow. This is the lower limit of fully turbulent flow, let us say. Fully turbulent flow typically happens after about 5,000, 6,000. So in the lower end, around 10,000 or so, the length required for development is about 60 times the diameter. And when we reach about 50,000, that is a very highly turbulent flow, then this length shortens to about 10 diameters. So this is very short. So suppose I have a let's say a 2-inch diameter or 5 centimeter diameter pipe which is carrying water, then 10 diameters of it is only let's say 5 centimeters here, so 50 centimeters. So within about half meter of the length of the pipe, the flow becomes fully developed. So if I have a 300 meter pipe, the developing length of the pipe, LDH, is much smaller as compared to the actual length, and therefore you don't really need to worry about the extra pressure drop that happens in the first half meter, and you can calculate the total pressure drop in the entire pipe, assuming that the flow to be fully developed in the entire pipe. In the same fashion for heat transfer, if the flow is very highly turbulent, then you don't really have to consider the entry length unless the pipe is extremely short. Okay, so that is the thing that we will be looking at. So in the case of LDT by D, this again will be 0.05 RD dPr in the case of laminar flow. So when the Prandtl number is, let us say, 1, that is for air, and the Reynolds number is 2300, then again you have close to 125. If I take it as 2500 approximately 120 to 125 diameters as the thermally developing length. And if the Prandtl number is greater than 1, then it takes even longer, because PR is greater than 1, so it's greater than 125. So suppose PR is 7, like for water, then it will be this times 7 will be the total length required. The LDT by D will be 125 times 7, so that many lengths will be required for the thermal boundary layer to develop. Whereas if I can take the Prandtl number plot, so this is for laminar flow. In turbulent flow, again, irrespective of what the substance is, it is 10 to 60 diameters for full development. So this is the development length that we need to understand. Now Nusselt number for fully developed turbulent flow. Okay, so this can be calculated using the Stanton analogy, or rather Colburn analogy. Okay, irrespective of whether the flow is laminar or turbulent, you can use this. In turbulent flow, Cf by 2 is known to be 0.023 divided by RE D to the power of 1 by 5 for a circular pipe. Okay, so by Colburn analogy, this should be equal to JH, which is Stanton number into PR to the power of 2 by 3. Okay, which is nothing but 0.023 divided by RED to the power of 1 by 5 is actually equal to the Nusselt number NUD divided by RED into PR multiplied by PR to the power of 2 by 3. So if I take this, then I can write NUD is actually equal to 0.023 into RED to the power of 4 by 5 into PR. Okay, and this NUD is nothing but H into D by K, where K is the conductivity of the fluid, and this H D by Kf is the enhancement in heat transfer coefficient, enhancement in heat transfer by the presence of flow, and that is given as 0.023 RED to the power of 4 by 5 Prandtl number. That is by Colburn analogy. This is slightly modified to give what is called the Dittus-Boelter Okay, this Dittus-Volturi equation is actually an experimentally derived expression. It basically says, okay, this is P r to the power 1 by 3. Sorry. Okay, so the Dittus-Volturi equation basically just modifies this as nu d is equal to 0.023 remains the same, Red raised to the power of 4 by 5 remains the same. It says Reynolds number raised to the power of n, where n is equal to 0.3 or 0.4 depending on whether the fluid is being heated or cooled. Okay, so in case of the fluid being heated, that is when the wall is hotter than the fluid. Okay, so when T wall is greater than T mean, you get 0.4, and when T wall is less than T mean, you get 0.3. Okay, so this is the only change that Dittus-Volturi introduced, and this is one of the most popular correlations that is commonly used for finding out Reynolds number or heat transfer coefficient or heat transfer to a pipe in turbulent flow. Okay, so in the case of laminar flow, you found that the dependence on RE and PR is non-existent in fully developed flow. You get just a 3.66 for constant wall temperature, 4.36 for constant wall flux, and any other constant number for other kinds of boundary conditions. Whereas in the case of turbulent flow, it depends on Reynolds number and Prandtl number in this fashion, and the 1 by 3 is replaced with 0.3 and 0.4 by Dittus-Volturi in order to match the experimental data well, and so you get this. So this is the Reynolds number in turbulent flow for fully developed flows. Okay. The last thing that we look at is non-circular ducts. Okay. So we'll use all the relations that are used for a circular duct for also the non-circular ducts, except that we have to calculate an equivalent diameter called the hydraulic diameter. So we call this the DH. This is defined as 4 times the area of cross section divided by the perimeter that is wetted by the presence of duct. So for laminar flows, we said that the constant Reynolds number at fully developed region will change with the geometry of the non-circular duct. So let's look at some numbers very quickly. Laminar flows. So in this you have the constant wall temperature and the constant heat flux cases. So if I look at the geometry, if it's a circular duct, constant wall temperature is 3.66, this is something we saw, and constant heat flux is 4.36. And similarly, if it is parallel plates duct, the constant wall flux is 8.23 and constant wall temperature is 7.56. Okay. If it's a square geometry, the constant wall flux is 3.61. This is always slightly higher than the constant wall temperature case, 2.98. And if it's an equilateral triangle duct, then it would be 3.11 for constant wall flux and 2.47 for constant wall temperature. Whereas in the case of turbulent flows, you still use the Dittus-Volturi equation. Nu dH is 0.023 Re dH to the power of 0.8 Prandtl number to the power of n. Okay. Now this Reynolds number is defined in terms of dH and Nu is defined in terms of dH. Let's look at that. So Nu dH is nothing but H into dH divided by Kf. that is equal to 0.023 REDH raised to the power of 0.8, that's 4 by 5 into PR to the power of N, where N is 0.3 or 0.4, 0.3 for cooling and 0.4 for heating. Okay, it's the same thing. Now REDH is defined as rho into U bar into DH divided by mu, where DH is defined as before as 4 area of cross section divided by the weighted perimeter. So this is your expression. So the turbulent and laminar Nusselt numbers therefore can be obtained using the expressions that are given. And as we mentioned, in all of these cases, the developing region would have a higher pressure drop and a higher heat transfer coefficient as compared to the fully developed region. Okay, so that brings us to the close of today's lecture. So in today's lecture, we basically learned that just like hydrodynamic development happens, there is also a thermal development where the thermal boundary layer grows. So for simplicity's sake, we took a hydrodynamically fully developed flow and analyzed it for thermal full development. The length required for thermally fully developing a flow from the point where the boundary condition changes is given by LDT divided by the characteristic dimension, let us say 2H for a parallel plate channel or D for a circular duct, would be given by 0.05 times RED into PR or RE2H into PR. Okay, so that's a change that comes from there. Earlier it was only Reynolds number, here it's Reynolds number into Prandtl number. And we found that for laminar flows, the Nusselt number goes to a constant of the order of 1. And we found that for a circular duct, the value is 4.36 if the wall flux is constant, and 3.66 if the wall temperature is constant. We also looked at the temperature profiles, heat transfer coefficient profiles, and the pressure drop profiles for all of these cases. And we found that in the developing region, the pressure drop and heat transfer coefficient are higher than in the fully developed region. We also looked at expressions that are available for turbulent flow. We introduced the class to the Colburn analogy and the Dittus-Boelter correlation. There's a minor difference in the power of the Prandtl number in these two. And we said that for non-circular ducts also there are constant values of Nusselt number that come for laminar flow, and we showed some values. Okay, so that is where we end. So with this we come to the close of what we wanted to introduce to you in convective heat transfer in this course. In the next couple of sessions, maybe we will do some problem solving. Maybe we can do that in person when we meet in the class. In between, now we will also have one more tutorial sheet on convective heat transfer, and in about a week's time I'll also upload the tutorial solutions for the convective heat transfer cases. Okay, so then when you come back, we'll need to have the major test, which will be merged with the minor test, because the minor test could not be held and it's not part of the schedule. So the evaluation in the major test would contain a couple of questions which would act as a minor test evaluation, and then the major test. So we'll plan that and announce it as the time comes. So now the evaluations that remain are your tutorials and your class participation and attendance. Now attendance component would be difficult to evaluate in the period of absence, in the period when the institute was closed, but we will count the attendance when the classes resume. So the number of classes that you attend there and the number of classes you attended before the institute closed together can count for the attendance part. And that's about the course. So we'll close the course here, and we will discuss problems and tutorials when we meet in the course again. If you have any doubts or difficulties, you can post it on the discussion groups that have been opened in Moodle. I have not seen too many questions in that so far, only 1 or 2 questions in each module that I have found. Please make use of that and study. And let's meet when we meet again in July, and we will try to proceed and wind up the course in a successful manner. And this time you have got 2 extra months time, so you can actually study these topics leisurely and understand and do the examination with proper understanding. Okay, we'll stop here, and we'll meet when we meet in July. We'll meet each other in person in July.